In our next section, magnetism, in the chapter 27 discussing magnetic fields, we're going to take up the section 27.3 on magnetic moments. Remember, we were talking at the beginning of this chapter about how magnets do not have magnetic monopoles, that is, single poles that are north or south poles. So you can't have a box with only a north pole in there. If you've got a box that's got a north pole in it, it's got a south pole in it too. They always come in pairs. And so we need to understand how we talk about those moments. So this will have a lot of analogy to the section on electric dipoles that we discussed previously. I'm going to remind you what an electric dipole is, because it's always good to review. If we had a positive charge and a negative charge together, they're equal and opposite, and maybe this is plus 5 coulombs, and these are separated by a distance of 4 meters. Then the positive charge times the distance between them gave us what we call small p, the electric dipole moment, which was defined as the charge q times the distance, and in the direction of the distance. So this would be 5 times 4, which would be 20. And that's that value of 20 gives us this value of P, called the electric dipole moment. And what can happen with this? Well, we can look at where this is in an electric field, for example. If it's in an electric field in this direction, you'll recall that this made this want to turn. And so there was a torque on it, so we could compute torque, and we could also compute the energy that had, and I'll let you go back and review that. Well, now in talking about the magnetic dipole moments, it's a little bit different because we don't have north and south poles that are separated. But the magnetic dipole moment, we use the symbol as defined by the symbol mu, the Greek letter small mu, and it's defined as the current that flows around a closed loop times the area that is enclosed by that loop. And it has a direction, and the direction here is defined by the area perpendicular to the area and in the direction of the right-hand rule. I'll put right-hand rule here. So, for example, let's imagine, the easiest way to figure this out is to work a simple problem. Let's imagine we have a rectangle. It's 2 meters by 3 meters. And it has 7 amps going around in a circle. Well, how do we compute the magnetic dipole moment? Well, mu is going to be equal to the current, which is 7 amps, times the area of the loop. Well, this is a rectangle, 2 by 3, so this is going to be 2 times 3 square meters. So this would be 3 and 3, 6. 6 times 7 is 42, and this is amps times square meters, and this would give us mu. So that's how we calculate our magnetic dipole moment. This is the critical formula right here that you have to remember, just like you remembered this one in the past for electricity. That magnetic dipole moment points in the direction given by the right-hand rule. Again, you imagine the perpendicular to the area, and if I take my fingers and make them go in the direction of the current, this would point in the upward direction. If the current were going this way, then I would have to wrap my fingers that way, and it would go in the downward direction. So this is 42 amp square meters out of paper. Well, it turns out that all magnetic fields actually arise from these loops of currents, and you can note here how this right-hand rule gives the direction to the loop as I just described. These little dipoles, a loop of current going around some area, are the tiny magnets, and therefore they feel a torque when they're in another magnetic field. The torque on a magnetic dipole is given by torque is equal to mu cross B. Now, do you remember this is magnetic? Do you remember also that our torque electric was equal to P cross E? So if you remember these previous formulas on the torque of an electric dipole in an electric field, you have the same torque given by the magnetic dipole in a magnetic field. And so you can figure out what this is. You would, if this were in a, say, a magnetic field pointing, say, in the perpendicular direction, like maybe there's a magnetic field this way of 5 teslas. Then, in fact, you can see that since this goes upward, the mu comes up out of the paper, the cross product of it with this one, which is 90 degrees away, is a 90-degree angle, and the sine of 90 degrees is 1. So we would get our mu, which is 42 that we just computed, times our B, which is 5. And that would give us our torque if you multiplied those, and it would be times the sine of 90 degrees, which is 1. And so we don't have to worry about the sign there. Now you can say, which direction is that torque going to be? Well, if mu points upward and B points to the right, we again use the right-hand rule. And mu cross B would give us this cross this, which would mean in the upward direction. So it's going to turn this way. It's going to try to take that loop and turn it in this direction. And that's where we get our torque. Likewise, we can talk about the energy, and the energy that that little magnet, that little dipole moment has, is going to be given by minus mu dot B. And again, you can figure out what that dot product is, given the magnetic field. The magnetic field's a cosine. If these were, that would be 0. That's just kind of the standard for the problem that we just did. See if you can work that, because mu comes outward, B goes this way, and so the dot product is the cosine of the angle. Cosine of 90 degrees is 0, and so that would tell you that that energy is 0. It's kind of a reference energy. We had exactly the same work up here. This is U, potential energy magnetic. The electric was equal to our P dot B with a minus sign. P dot B, just like this is mu dot B. And so there's an exact parallel of this formula with the 1 in electricity and this formula with the 1 in electricity. So this one, and this one are the 3 new formulas, defining the magnetic dipole moment, defining the torque on it, and defining the energy which it has.